Welcome everyone. It's a pleasure again to have Jaikumar here, and he'll continue on with his series of lecture on classical and quantum information.
So yeah, thank you for coming back. So let me quickly review what we did last time and try and address some of the questions that I did not adequately address last time. So we started with a source, and the source has some symbols, n of them, and associated probabilities. And we were talking about the source coding problem. So we were thinking of transmitting information from Alice to Bob using bits, zeros and ones. And the idea was that Alice is going to observe the outcome of this experiment, and based on what she sees, she will transmit the code word corresponding to that outcome. Which code word corresponds to which outcome is determined in advance by Alice and Bob, and they try to do this in order to optimize or minimize the communication. Okay. And what we would like to know is how should we arrange these WIs so that they are prefix free, so that as soon as the word arrives, Bob should know that what was transmitted. Okay. So there was some technical condition about things being prefix free. Let's not discuss that too much today. But the goal was we wanted to minimize the expected cost of transmission. And by this I meant the number of bits in the word WI. And the answer to this question we declared, or we defined, to be T of X, that is the transmission cost what is the best way to transmit the information that Alice receives on performing this experiment. And we proved a theorem, or we associated T of X with a quantity, and it turned out that this turned out that this transmission cost for sending X is very closely related to the entropy of this source. So in some ways, this gave us a justification, at least from an operational engineering point of view, for regarding entropy as the amount of information in this source. So this is where we started. But there was something not quite satisfactory about this characterization of transmission cost. And let me tell you what made us uncomfortable. If you look at this source X, which is the outcome of or which is a fair coin. My logs are all to the base 2. So in this case, the entropy of X is 1. And to transmit the outcome of a coin toss, Alice just needs to tell Bob the coin toss. Yeah, I saw a 0 or I saw 1. But then there is the biased coin, and which takes 0 with probability, let's say 1/4, and 1 with probability 3/4. And if we ask what best Alice could do to transmit this information, there's no error, nothing is allowed. No errors are allowed. Bob needs to decode absolutely correctly, faithfully. Then again, we see that the transmission cost remains 1. Yeah, you cannot do anything better than 1. But the entropy in this case was something like 0.811. So the question is, this is all very good, but does 0.811 mean anything from an operational point of view? Is there an operational problem, an engineering problem we can cook up for which 0.811 is the answer? Okay, so let us just, and that problem should have something to do with this biased coin. It turns out that if we, this is called instantaneous. We see a symbol, we transmit its code word. Shannon observed that we get some advantage over instantaneous coding if we block symbols together. That is, especially if we would like to perform this experiment several times, and Alice would like to send the outcome of all those experiments, then it's not such a great idea to take the first outcome, send its code word, second outcome, send its code word, and so on. Instead, they should first agree on a certain block length and decide to encode all possible occurrences for that block length. So let me explain. So this led us into understanding what typical outcomes look like. I'll come back to the biased coin, but when you have a source, X, and we draw independent samples from that source, we get sequences. And each of these sequences has a certain probability. Yeah, the probability that X1 came up, and X2 came up, and Xk came up in the corresponding experiments. Now, most of the probability resides on what we last time called typical sequences. And we saw last time that the probability that where this little X bar is typical looks like so. There are some typical sequences, and let's just review what a typical sequence is. A typical sequence is a sequence where the letter A1 appears roughly P1 times. The letter A2 appears P2 times. We don't insist that the letter A1 should all appear in the beginning and then A2 should appear. A1 appears P1 times, A2 appears P2 times, AN appears Pn times, and they are jumbled in some way. And all possible jumblings will still allow us to call this sequence a typical sequence. That is, the empirical distribution of this sample is pretty close to the true distribution. Then we call it typical. And there was an epsilon parameter which used to govern how close this empirical distribution needed to be to the actual distribution. Let's not get into that. But when you look at typical sequences, it turns out that typical sequences have probability which look like 2 to the power minus k h of x. Furthermore, most of the probability lives on typical sequences. So I'm calling this the typical set, the set of typical sequences. In other words, the number of sequences in this typical set, is approximately, well, this is almost probability 1. Each of the typical sequences contributes about this much probability. So it is 2 to the power k times. So this was a rough analysis we did of the situation when we draw independent samples from the source k times. And the probability outside is negligible, yeah? Much less than delta. We can make this delta go exponentially small in k. Okay, let's say something like that. So here is an alternative strategy for Alice, or Alice and Bob together. They know that they're going to be performing this experiment. So what they decide is that, look, Bob tells Alice, if the sequence is not typical, don't bother, or send me some arbitrary message. I don't mind if something wrong, if I decode it incorrectly. But to each of the typical sequences, we will assign a separate code word of the same length. So how many bits do we need to invest if we are told that there is nothing but typical sequences? You don't need to bother about the rest. Then since there are these many sequences, so each sequence is associated with a word of approximately k times h of x. There are lower order terms, k times h of x plus some lower order terms, but the coefficient of k is h of x. And then they do the transmission. Question? Sorry? Why the 1/3 came up? Yeah, so this is not very important. The point is, so we had this sequence x1, x2, xk. Yeah. Now, how many A1s do we expect in this? About k times probability of A1 in the original scheme, let's call it PA1. K times PA1 is what we expect. Yes. Now, but it won't be exactly k times PA1. It will be a few standard deviations off. Okay, so it will be k times PA1 plus or minus square root k. Okay, but what's the probability that it is k times PA1 plus or minus, say, k to the 2/3? well, it will go exponentially down in k. So this k to the 1/3 was something I chose arbitrarily. Yeah. So just to account for the fact that when you perform experiments, things don't come out perfectly in, according to the proportion. There is a small deviation, but we tolerate that deviation and still call the sequence a typical sequence. Yeah, so we try to make sure that this probability goes to 0 as k goes to infinity. That's all. But, all right, so if this is what Alice and Bob adopt, then what is the conclusion? Yeah, so to transmit the outcome of k, she needed k times h of x bits. So per symbol, she's using h of x. Now let's come back to this situation. If we were in too much of a hurry and we were trying to transmit things as soon as we saw them, we needed 1 bit per symbol. But if we allowed ourselves to block k of them, but with negligible error, we give up on some possibilities, but their probability is going down exponentially in k. The combined probability of the outside region is going down exponentially in k. Then we actually transmit only 0.811 bits per symbol. Okay? And this is tight in the following sense, that if anybody tries to transmit this information with less than h of x bits, then they will make probability of error going to 1. Yeah. Any scheme where Alice spends, say, less than h of, for some positive eta, if you go, yeah. So the way we should perhaps understand it is by drawing some sort of a graph. As k becomes large, and we plot the best scheme to transmit information, we fix our error probability extremely small. Then if you're at h of x, if you plot the probability of error, if you do a rate less than h of x, then your probability of error is almost 1. And at h of x, the probability of error is almost 0. So in some sense, this is the place where we go from impossibility of transmitting the information to absolute certainty of sending the information. And that sort of gives us more confidence that h of x should be regarded as the information in the source. So this is what I should have said last time. As k goes to infinity. As k goes to infinity, yeah, so for a finite k, I mean, you people know how to interpret these graphs. It is probably going to be like, yeah, like this. And as k goes to infinity, it becomes sharper and sharper. And yeah, and eventually it starts looking almost like this. So this is what Shannon discovered, and this is called Shannon's source coding theorem. Those two statements together, if written properly and mathematically, would amount to Shannon's source coding theorem. That is, above h of x, you can transmit with almost certainty. And below h of x, things are hopeless, if k becomes large. Again, when I say question. Yeah, so so first of all, yeah, so if you try, yeah, so if I try to take some other set which captures a good amount of probability, well, this set already has most of the probability, okay? So what lives outside will be essentially measure zero as k goes to infinity.
Yes, sir. I have a question.
Yeah, there is nothing special. It just says that typical sequences are special, and we just need to focus only on them. Okay. Now, but maybe I should correct myself a little bit. Typical sequences are not the most popular sequences. For example, in this scheme, a typical sequence has 1/4 0 and 3/4 1s, and they are probably located all over the place. But which is the most popular sequence? This was a question that was answered last time. The all ones. Yeah. So if somebody could be greedy, not quite follow what we are recommending, and say that no, this sequence is giving me a very high probability, let me go and assign a code word to it. No problem. Yeah. And you could go and assign code words to sequences which are heavier than typical sequences, heavier in ones than typical sequences, but it is not going to change your probability too much, because they combined together do not have much probability. Okay, so this is what I said about h of x. The next thing almost towards the end, we talked about conditional entropy. So let me review what we said last time. With some they have some joint distribution. The probability that x is A and y is B is this, they're not necessarily independent. Then we define something called the entropy of y given x. And there was a formula for it. And let me this time write down the formula right away. It was the probability of A and then the entropy of this was the definition of conditional entropy. Now, why this is a reasonable definition of conditional entropy, we will see soon. But let me explain what I mean by this. I have not defined everything that I'm writing, but you understand. When I write PB given A, I mean the probability that Y takes the value B, given that X has taken the value A. So this is actually an honest to God entropy. It's the entropy of the conditional distribution conditioned on X taking the value A. But we don't just add up those conditional entropies, we take their average. Average according to the probability that X takes the value. This PA stands for probability that X takes the value. So let me draw a picture. Imagine that there are several possibilities for X. These are the various possibilities for X. Let me call them A1, A2, AN. And each of them has an associated probability, P1, P2, Pn. Suppose we are looking at AJ. AJ is one of the outcomes of performing the experiment on X alone. Yeah? And then when we observe Y, Y can take various values B1 to B, let's say M, with some associated probabilities, and those are these probabilities. Yeah? This with AJ. So this, if we ignore the rest of the picture, this is a probability distribution. It's a probabilistic scheme like that. It has its own entropy. And that entropy is what I call HY given X equals A. So we have X equals AJ. We have fixed the value of X at AJ, and then we are trying to observe how much entropy there exists in the random variable Y. And then we take the average of these quantities, and that is what is called conditional entropy. So is this okay? Yeah. Now, what does conditional entropy count? Just like entropy seems to count the number of typical sequences, what does conditional entropy count? So it will be important for us to understand what conditional entropy counts, because the next theorem, that is Shannon's channel coding theorem, which we haven't discussed yet, I will make use of that fact. So let me try to explain what conditional entropy actually counts. So fix an X. We did this in a hurry last time. And suppose that is, the empirical distribution inside of X bar are these numbers, PA, the same numbers PA. That is a proportion, PA of all these symbols are A. A1, A2, A3, AN appear with the right proportion. Let's just assume. Now, the question we ask, so there is this joint distribution PAB. We first observed X, and it turned out that X had the right proportion of symbols. Now, so we have X1, X2, Xk. the slots for X are taken. There are slots remaining here for Y's. How many ways can we fill these slots here so that the resulting sequence here will be called Y bar? So that when I look at this combined sequence of pairs, the pair AB appears this times K times. With a little thought, you'll realize that let us focus on those places where, say, A appears. And under it, the number of ways we can fill things up using our understanding of typical sequences. So the answer, we did this last time, should look like we take the probability over all possible symbols. So look at places where little a appears and ask how many ways are there to fill up the things below it. Well, that number, if our previous understanding is correct, must look like except that this is not K, it should be so if you perform some experiment K times, then the number of possibilities is K times the entropy. But we are doing that experiment now only PA times K times. So the number looks like this. And if you rearrange this, this looks like 2 to the power summation PA H of Y and this is conditional entropy. So what's our understanding of conditional entropy? Once you fix a typical sequence for X, how many ways can you extend it to a pair of sequences so that combined they look like jointly typical? They look jointly typical with respect to the given distribution. That number is, so this is what I wanted to say in review of what we did last time. Yes, I'm missing a case, sorry. Yeah, so I meant to write this times K outside. Yeah. So the number of ways of extending X by a Y, of course, the number of Ys grows exponentially in K. The coefficient in front of K is the conditional entropy. So the setting is the following. Question, sorry. That's right. That's right. Correct. Yeah. I don't think there is a big difference in the rate at which they go to 0. They will all be exponential in K. yeah, it doesn't matter. Yeah. But maybe, yeah. But since you talked about joint typical sequences, let me just write down one equality and then we will move on. Yeah. So if you have a pair of random variables x and y, it has its own entropy, and that entropy governs the number of jointly typical sequences. But these jointly typical sequences, we could imagine, were generated by first picking a typical sequence for x and then extending it by a typical sequence, a y bar, so that they together become jointly typical. So from this, we basically immediately get I'm just saying that I take k times the number of jointly typical sequences must grow something like this. Number of ways of choosing x bar grows like, and the number of ways of extending a given x bar by a y bar roughly grows like k times h of y given x. And if you, yeah, these must be roughly equal. If you take logs, divide by k, and do things like that, you should get this. But as you probably already see, if you look at the formula and write it out, there is a formula for this, there is a formula for this, there is a formula for this, and they just match up. But this gives some sort of a combinatorial justification why it was inevitable that this equality should hold. This one. So we have this probability distribution for pairs. Suppose we sample pairs. Yeah, so first we get x1, y1, then we get x2, y2, xk, yk. Then let's focus on one AIBJ. How many times should it appear? Well, k times p of AIBJ. Okay. Or h of x comma y is that formula that I wrote for entropy, where okay, so maybe I should just write it down. So h of xy, yeah, I should have written this, is summation PAB log 1 over PAB, summing over all possibilities for AB. Okay. So it is as if I regard xy as a composite random variable. That's all. But then when I start discussing their typicality, etc., if you follow through with the kinds of considerations we have been adopting, you will see some equality like this show up with lower order terms. And then when you take log, divide by k, and take k to infinity, this should pop out. I'm being a little vague, but just that is the general feeling of entropy you have in this probabilistic setting. Thank you. Yeah. So let me now describe the setting of Shannon's next theorem. So you still have Alice and Bob, and there is a channel. Now, what's a channel? It's given by so Alice is allowed to feed an A to the channel, a symbol from this set, capital A, and what will come out is a symbol from this set B. Yeah? But things are not deterministic. So far, when we were discussing our transmission costs, etc., we said when Alice sends a 0, it shows up at 0 at the other end. But now, we are talking about channels that might change what you send. Okay? And we are keeping things very general. That is, the input alphabet is A, the output alphabet is B. So the way one could perhaps think about it is that this is the input alphabet A, and this is an input alphabet B. B could be larger than A or smaller than A, we don't know. And when we send the symbol A into the channel, various things could appear outside, but we know the channel characteristics. That is, when A is sent, this B will be received with probability B. We are told this. Okay? And we would like to know how reliably Alice and Bob can communicate using this channel. Okay, so we'll need to say what we mean by that. Yeah. So suppose there are sorry, just hold on. So I'm using a letter R here. Later on, it will become clear why it should be called R. But there is a certain number of sequences, favorite messages that Alice wants to send. Yeah? And she would like to send them through this channel. How? She would encode each of her messages. Yeah? M1, M2, M2 to the NR. Yeah? There are these many messages that Alice has in mind, and she would like to send them through this, transmit them to Bob. So when M1 is sent, so M1 will be encoded as a sequence of A's and sent through the channel. And when that sequence of A's passes through the channel, if the first symbol is A1, one of these symbols will appear. The next symbol is A2, one of these symbols will appear, and some string of n symbols or certain number of symbols will show up. That symbol needs to be decoded by Bob back to the message. Okay? So a coding scheme looks like this. There is this channel which has its characteristics P, Y given X. There is the encoder, and there is a decoder. And into the encoder, one of the symbols, M1, M2, let me just call it capital N for now. One of these messages will be sent to the encoder. Encoder will convert it into a code word. But the code word will be in over the alphabet, input alphabet A. Yes? And this particular channel will transmit to the decoder, but according to this rule. Yeah? And then the decoder, so this is the code word. This is called the received word. And this is the output message M prime. So a certain message M, one of these was sent, and the decoder does something, he obtains M prime. Okay? And when do we say that this is a reliable scheme for encoding, for transmission? If for all M, M1, yeah, any of these m's, the probability that m prime equals m, we would like to arrange things so that Bob gets what was meant to be sent. Okay. So it's and if we want to send n symbols here, n messages, one of these n messages, we don't want to send all of them. We were told that one of these messages will have to be sent, and you should make provision for each of these messages. But when a particular message here is sent, the decoding invariably should deliver the same message. Now, one can imagine that if you have n things, you will have to produce code words of various lengths, or at least some long code words. And what we would like to know is that if there is a variety of n messages that we want to send here, how long do our code words have to be? How long do they have to be? That is, how many times do I need to use the channel so that I can communicate reliably? Yeah. So this n, I mean, when I have 1 to n, I will say that this is, I'm sending log n bits. Yeah. So, you understand? There are n possibilities, so it amounts to saying that I'm sending log n bits. And to send log of capital N bits, how many uses of the channel do I need? Okay, and that will be considered the rate of communication. That is, the number of bits you send per channel use is called the rate of communication. And what we would like to know is, given channel characteristics, how do we determine the optimal rate of communication? That is the best rate of communication that this channel can support. So please ask, I've not been questioned.
Does your channel in general depend, like here the delta depends on the message you are sending? Should delta depend on M?
No, so we would, okay, so there is a prescription. The person who wants this transmission says, please do this with delta equals 0.00001. So it's prescribed, okay? Now, for every message that you try to transmit, the output should agree with it with probability, whatever, 0.99999. Okay, and given this delta, you have to design your encoder and decoder so that you get the job done. Yes, this delta is a common delta, and this should work for every message. That's all. Channel is another name in communications engineering for specifying the conditional probability matrix. If you tell me the conditional probability matrix, that is the channel. Or if you like, if you draw this picture, that is the characteristics of the channel. That's it. Okay. They are not part of the channel. Okay. So once again, channel is what sort of reliance gives us. Then our engineers work, build the encoder and the decoder. Okay. The boss tells us what reliability he wants. And based on this reliability, we design the encoder and decoder. And the boss says, I will be sending one of these n messages. Please make provision for this. Okay. Now, and the boss is pleased with you if you manage to use the reliance channel as few times as possible and still maintain provision for all these n symbols. Okay. Is that all right? Question?
Were 0 and 1 just, not string of zeros and ones.
It is not important to us. So you could say that, I mean, now it has stopped, but in olden days, there used to be these things where you could send messages by telegram, people greetings and things like that. So it could be long sentences. There are n different messages that you want to send, okay? But I agree with you that so that we have common units for judging everything, let us say that your messages are all log n bits strings. So they are all elements of 0, 1 to the power log of n. You can imagine that if there were some other n messages, we can just tweak the encoder so that they work with those messages. In the end, what matters is what is fed into the channel. And similarly, the decoder can play games and change the received word back to the message. Is this okay so far? Question?
Can you elaborate a bit on like what a physical model for this would be? Like, is it I want to send a message, let's say I encode it in my telegraph code, but then my telephone line will be more faulty for points than for lengths, for example. Is this
is more faulty for?
More faulty for the dots than for the long signals?
Exactly.
Okay.
So maybe I should give you some examples. This doesn't. So the input alphabet is 0 and 1. Yeah, you could feed a 0 or a 1 to the channel. You will get a 0 or a 1. But if you feed a 0, you will get a 0 with probability 1 minus epsilon. But with probability epsilon, the channel will change it to. And if you feed a 1, with probability epsilon, it changes it to a 0 with probability 1 minus epsilon. So this is called the binary symmetric channel with crossover probability epsilon. This is called the binary erasure channel. So when you send 0, with 1 minus epsilon probability, it goes out as 0. But there is a small chance that what you sent got garbled and some funny symbol substitutes it, or it gets erased with some probability. So here the input alphabet has 2 symbols, the output alphabet has 3 symbols. Okay. It's okay. Question? No, it doesn't have to be the same. The channel has its randomness, and I allow my decoder to this, but most of the time when M is sent, what is recovered should be M. So what does, so I would like to write down Shannon's theorem, but I have a feeling that you'll be able to tell me what it is yourself, or we can work towards it. So let us say yes. a to the power. So Alice is going to feed a sequence of length k into the channel, and the channel is going to output something of length k, but from this alphabet. Yes. Now we are wondering what is the best strategy for Alice. Yeah. So Alice is going to choose some special n code words. She's going to choose some special code words here. And when this code word is sent, when this sequence of length k is sent, we don't know, some sequences might be received on Bob's side. But for most of these sequences, Bob should map it back to this, because he should be able to say, oh, this was sent. There might be some sequences which can be generated for two different code words. Bob has to decide which one to choose, probably the one which has a greater chance of generating this. Okay. Let's just work with such strategies. Okay. So now, these are some code words, and let's just see, they are of this form. Each of them has this form. And each of them might have its own type. Some of them may be heavy on A's, the others A1. Some of them have many A1s, some of them have many A2s, etc. Because there is no probability distribution right now. The only thing we are given, as somebody observed, is conditional distribution. The distribution for X is not there. Yeah, there is no distribution for X. But we will turn things around and we will say, look at all your code words, the code words that Alice is using. Yeah. So let's just understand the limitations that Alice is working under. So look at the code words that Alice is using, and each of them has its own empirical distribution. Okay. Now, if you have k sequences of length k, the letter A1 could appear, at most k times. So it has only a certain number of possibilities. It could appear 0 times, 1 time, twice, thrice, or k times among these. So the number of different empirical distributions
and these sequences need to be typical sequences or any sequence?
No, they are just any sequences.
Okay.
Yeah? So they are just arbitrary sequences. I mean, we don't want to constrain Alice. Alice has said, I get my job done, and these are the code words I'm using. So she says, I use this code word for the first message, this code word for the second message, this code word for the last message. Okay? And they have each of them has its own type. Now, the number of types is at most is clear? You see, a type is determined by how many times A1 appears, how many times A2 appears, how many times A3 appears, how many times AN appears. A1 can appear in 0 times, 1 time, up to k times, that is k plus 1 possibilities. A2 can appear k plus 1 with k plus 1 possibilities. So this is an overcount, but this is the total number of types. Yes? But the point is that this number looks like 2 to the power n. Yeah, there's only a log k here, okay? And we are thinking of transmitting where it is like 2 to the power k times some rate r, okay? So this doesn't matter. So what do I mean by that? So n divided by 2 to the n log k plus 1. Of these code words, there is a good number of them which come from the same type. There are these many code words. There are only these many types. Just what's the pigeonhole principle. This divided by this must have the same type. So basically, even though Alice is using many code words, most of the code, or a good fraction of the code words, are of the same type. So let us focus on that type, and let us say the type is P. That capital N was somewhere M1 to M, this capital N. Okay, so there were N possible messages. Out of them, each of them had its own private code word. That code word had a type. Many of those code words had the same type. Which one? There is no direct relation. Small n was the alphabet for, yeah. So in this channel, small n was 2. Okay, yeah, so I'm sorry to use, yeah.
Capital N is the number of things that Alice can send.
Yes, number of different messages for which.
Some alphabets repeatedly.
Some letters repeatedly, yeah. 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 That's right. Yeah. I mean, she decides to encode her messages as sequences over this n-letter alphabet. Over this n-letter alphabet. So there are capital N different sequences here. Out of them, a good fraction of them come with the same type. They are the same type. Now, when you transmit one of these, what you will receive here, no, please. That's right. That's about how many times a certain letter is. Exactly, exactly. A type is like the empirical distribution. Yeah, so you drew samples from this distribution and then said, how many times does A1 appear? No. Okay. No, let's look at x1 to xk, one particular sequence. In that, let me tabulate how many times A1 appeared. A1 appeared K1 times, A2 appeared K2 times, AN appeared K little n times. Yeah. Look at this one. In that, A1 appeared K1 prime times, and AN appeared Kn prime, and so on. Each of them has this data. Where this A1 appeared, as you said, I don't care. How many times it appeared is all I keep track of. Okay. Now, for each of these sequences, I write down this. Okay. But when I look at this, how many possibilities do I have for this composite object? This number K1 ranges 1 to K plus 0 to K. Yeah. So the number of such objects, we can call it a signature or the empirical distribution, is at most K plus 1 to the power n. Yeah. So if I look at this, many of them will say, oh, our data looks the same. We probably are different in arrangement, but overall our composition looks the same. Okay. That is to say, they have the same type. The word type I'm using for this. Okay. Yesterday I divided this by K so that these numbers look like probability, but yeah, apart from the fact that I don't normalize, this is what is type. Okay. So a good number of them have the same type and P, and when I write P, of course, I mean probabilities. Yeah, K, these numbers divided by P. Now, here is a sequence which has a certain type, and it is being fed into that channel, and out will come a Y1, Y2, to yk, because when x1 is fed into that channel, it will spit out a y1 according to the rules of the channel. And x2 will spit out a y2 according to the rules of the channel. The question is, how big is this? Well, when things are sent, this sequence has type P, which means it is typical with respect to P. Because in this case, we have turned things around and defined P so that this is typical with respect to P. When you feed this into the channel, what will come out will be jointly typical with respect to this. If A1 appears 7 times probability of B given A1, that many times B will appear under it. Yeah. So this will be jointly typical with this. That means this number grows like 2 to the power k times, where x is drawn according to, actually this is the main idea. So please ask if it's not clear. Yeah. So if I feed into a channel something of type P, a sequence of type P, out will come a sequence with k symbols from the alphabet B. Most of the probability will be focused on a certain number of symbols. And how many symbols? Certain number of sequences. And so Bob's idea should be that if I look at a sequence and it looks compatible with this, that means it is jointly typical with this, I should probably decode it back. That is the idea. Yeah. So now, but we'll come to that later. Yes. Yeah. So if Bob sees B1, B5, B7, B1, B5, yes, and instead it is B7, B5. I'm getting what I just wanted to shift this. Yeah, these two have the same type if I have not made a mistake. I've just cyclically, no, what did I do? Yeah, so this sequence and this sequence have the same type. Type means count how many times each symbol has appeared. Type doesn't require probability. It has the same type, meaning it has the same composition of symbols. Okay. Or if you say the empirical distribution here, what is the probability of B1 in this empirical distribution? 2 by 5. Yeah. 5, also 2 by 5. 7, 1 by 5. Okay, so that's why there is an empirical distribution or a type associated with this. All these have the same empirical distribution. It's just that they have the same symbols, but they appear at different places. We'll go this. But I don't really understand what I was doing before. I was just saying I wanted to understand how well Alice could exploit this channel. Okay, so any theorem like this where we try to determine the best rate of transmission will have two parts. How well can we do and how well can anybody do? So we will show that nobody can do better than this and we can at least do this much. And if we are lucky, the two numbers will match. We say we have a method to do this and we have a proof that nobody can do better. I mean, yeah, that is when we declare success in any engineering sort of theory. We say this is the best we can do and we also give a proof that nobody can do better.
You're saying that all these capital things have the same type?
Not all, a good fraction of them. It was n divided by n divided by, what was this, k plus 1 to the power little n of them have the same type.
Why is that? So k plus 1 raised to n is the total number of types.
Total number of types. Each of them has a type. Yes? I mean, think of type as a color, okay? So each of them has a color. There are only these many colors, and there are these many objects. So these many of them must have the same color. I mean, you have n shirts and only 5 colors. So n over 5 of your shirts must be of the same color.
Can
Question.
Can we say that all the elements in the this popular type has the same probability?
We have not even defined probability for x's, right? We only have conditional probabilities.
I mean, if all these different A1 to let's say AK are occurring same number of times, then the probability should be same, right?
They have the same empirical distribution, okay? Probability is the probability of something occurring in a distribution. We don't even have a distribution, but I think it's just a question of language. They all have the same empirical distribution, okay? Yeah. Sorry, how can these two be distinguished? No, Bob receives it. When Bob sees B1, he says, I did receive B1 before B5. In this, I received B5 before B1. So he's going to do different things. Sorry. So when this was transmitted, in this case, Bob saw B1, then he saw B5, then he saw B7, etc. In this case, he saw this, and his actions can be different for this. He could say, I would decode this to this and decode this to this. His decoder has that right to do this. Yeah, it's not as if the channel takes all the symbols, jumbles them up and says, do something with this. No, it gives him things in the same order. Okay, the channel doesn't do jumbling. Is it clear so far? Yeah. So there is, yeah, so meaning all these code words, the other code words are there, but let us say these code words all have type P. Then each of these sequences, when they transmit, they smear their probability over a region which grows like this. The total number of, so we are now looking at a distribution where X is drawn according to P, and Y given X is according to the channel characteristics. Yes, so you generate X according to P. So I'm just defining a distribution. So there is a joint distribution on X and Y where X is drawn according to P, the P that Alice chose. And then we think of Y as having been generated out of X by the channel characteristic. These are all distributions on A cross B. Yeah. So this is a typical sequence with respect to P because it has type P. This is jointly typical with X. So the combined XY, yeah, is a jointly typical sequence. And whenever you have a jointly typical sequence and you look at the second row, it is a typical sequence according to Y's distribution. Whenever you have a jointly typical sequence, the top part is typical according to its distribution, the bottom is typical according to its distribution. In fact, there is more. They are also jointly typical. Okay. So this particular set has size 2 to the power k times h of y. Because all these, for each of these things, there are 2 to the power k times h of y given x symbols and, possibilities, and they are all confined to this space of 2 to the k times h of y. So then here is what, if Alice and Bob have to do this decoding nicely, then these things should largely be disjoint from each other. Because if there is a large overlap, then that means we are looking at sequences that are equally likely to arise from two different code words. And then Bob would not know which of them was actually intended. Okay. So I'm just hand waving a little bit here. So finally, we can write down this equation. That n divided by k plus 1 to the power n times 2 to the power k times h of y given x should be for Alice to be able to do reliable communication. Alice and Bob to be able to do reliable communication, it must be the case that something like this must hold. Okay. So yeah, this is the time to ask question. No, you cannot define h of y just given conditional probability. So I have said take x according to p and then extend it. So what is the probability that y equals b is summation over all a, probability that x equals a times p of. This was given, and I agree with you that given this, I cannot define the probability of y. But I have also now extracted a particular popular type p. Once I fix this type p, I can extend it to define probability for y. Composed with. So you generate x and compose it according to the channel.
So can you tell how this equality will be saturated?
Sorry.
How exactly will this equality is saturated? The inequality that you have written over there.
Yeah. I mean, the point is, so it is that equality is already a hand-wavy equality because we don't require all these sequences to actually decode correctly to this. We are allowed to make errors on some delta fraction of them. Okay. So there are these neighborhoods of these code words. Most of the neighborhoods should be private to this code word because they should decode back to this. There are some parts of the neighborhood which are common, okay? And there we are making errors, but that common part should be at most delta. Okay. So I don't know quite how to answer your question, but I'm just saying that if Alice has to have any hope of being able to transmit information reliably, then some inequality like that must hold. And let us just play around with this. Yeah, if you just take logs, what do we get? Log of n must be less than k times h of y minus h of y given x. And then there should be some lower order term. Yes. Now, let us say we just redefine n to be 2 to the power n, k times r. Yeah. So So I'm saying Alice had n different messages, M1 to Mn, which means her messages were k times r bits long. Yeah? Log of n is k times r. So to send k times r bits reliably, it must be the case, yeah. So she's using the channel k times and she's sending k times r bits. Yeah. So if you, the rate at which she can transmit, the number of bits per channel use is limited by this number. Okay. Now what do we know about this number? This is the mutual, called the mutual information between x and y. But the question is which x? Where was the distribution for x? That something that Alice chose. So the correct answer, so what is Shannon's theorem, or at least one half of it, that the rate no matter which, try the best empirical distribution for x and compute this quantity. That will definitely be an upper bound on the rate of transmission. Okay, so let me try and. So the only thing we were given is the probability B given A, the channel characteristics. Find out the best distribution on input symbols on the set A so that this quantity is maximized. And what is this quantity? Well, you use that equation to define the joint distribution. Once you have got your distribution for on the A's, you use this equation to define so probability of x equals A and y equals B is PA, P. So this is what we are maximizing over. Find the best P so that the joint distribution that arises has the highest mutual information, highest. Now this quantity has a name and this is called Ix. Okay. And so this is how Ix colon Y, the mutual information, arises in communication engineering. Okay, that was the point. Okay. So the entropy H of X arises when we try to encode things without error. But when we are given a particular channel and we try to do this, try to understand how best communication can be achieved through the channel, the number Ix colon Y pops out naturally because of considerations like this, which I did not clearly explain, but that's what happens. There is only this much space, and you need to pack things which are this big into this much space. Yeah, you cannot pack too many of them, because then they will start overlapping, and once they start overlapping, errors will happen. Let's leave it at this qualitative stage. Now it turns out that the converse is also true. That is, if you use, so you maximize, you find the best P that gives you the best value for this, then you can generate codes using this information so that you can do reliable communication with probability of error at most delta. So, in fact, the same picture arises. So I'll just stop. So there is Ix colon Y. This is maximum over all choices of X. This is called the capacity of the channel. If you try to communicate below the capacity, if you try to send information below its capacity, you can do it with very high success. Probability of error will be very small. Probability of good decoding will be very high. The moment you try to do communication beyond the natural capacity of the channel, your success probability will go to 0. Okay, and that is Shannon's theorem. Okay, so that is the capacity of the channel is equal to the maximum over the choice of x of I, x. Okay, sorry, so it's a whole messy thing I did today, but please ask questions and I'll stop at this point. Correct. Yes. Yeah, can you say it again? Can you ask again? That's correct. So this was one type P thing, and it was this, yes. This X bar, yeah. So there was this X bar prime, and it had its own neighborhood, yes. No, all these have the same type, but even though their type is the same, the symbols appear in different places in them. The letters A appear in different places. So the sequences that are generated here, they are typical with respect to our new distribution, and they are jointly typical with a slightly different sequence. Yeah. But it is possible that there are sequences which are jointly typical both with X prime and X bar. And in those cases, Bob gets confused. Yeah, but if there is enough space here, then we can throw in enough of those neighborhoods so that these overlapping regions have probability at most delta. Okay, that is the second part of the theorem, which we didn't prove. I mean, yeah, that was not the plan. They don't necessarily have to have the different neighborhoods, but we will choose, we are not choosing all sequences of type P. Among the type P sequences, we will be choosing some special ones which are well separated, whatever that means, so that their neighborhoods don't clash. Yeah. See, the number of, yeah, maybe that's a good idea. Yeah. So the number of sequences of type P is 2 to the power k times h of x. Yeah, this is not the number of code words we have. The number of code words we have is 2 to the power k times this number. Yeah, so I'll just stop 1 second here. So the mutual information between x and y has sort of 3 formulas: h of y minus h of y given x, which is what came out of our calculations. It can also be written as h of x minus h of, and it can also be written as h of x plus h of y minus h of xy. Okay. If all sequences of type P were used, we would have got these many. But we actually get 2 to the power h of x minus, little less. That means of the typical sequences of the sequences which are of typical of type P, we sample only a smaller number so that even after they expand, they don't clash. Basically, we are picking the P to be, I mean, as, yeah, so that error correction works. So that these neighborhoods don't clash. And it turns out that how well we can do is controlled by an entropic quantity, h of x plus h of y minus h of xy. And that is where mutual information arises in communication theory. So that was the goal, yeah.
I'm a bit confused why this leads to the symmetric quantity between x and y.
Sorry, why it is symmetric?
Yeah.
Yeah, so, I mean, I don't have a, I mean, sorry, I mean, the formula is symmetric, at least this one. Yeah. Now, what should? Is common to them? No, but that is because I use the English word mutual. I mean, I use the word mutual and then insist, of course, mutual must be symmetric. No, but in this communication problem, this particular expression showed up. Okay. Yeah. Now, and when I kind of write it down, it looks like it is symmetric in x and y. So is there some other communication problem whose complexity I immediately see obviously to be the same? And there it would have been natural for me to write hy x. And then then if I do such a thing, then I have a combinatorial proof. I agree with you. At the moment, I do. Yeah, but the reverse channel has not even been given to me. This channel, I can only use in this direction. Yeah, I agree with you, yeah.
Why the backward channel is also, the optimal backward channel is also given by the same forward channel?
No, I mean, here the channel was specified and we were asked to make the best of it. And this quantity is the best we can do with it. That is Shannon's theory. Okay, but yeah, I don't know about how to. For this, there is a different interpretation of mutual information where that it should be symmetric is clear, but I'm not able to justify it based on this occurrence of mutual information in this theorem.
Channel capacity?
Yes.
I thought that the channel capacity is like you have to take an IID limit, but here it seems that you consider one-shot case.
No, it's not one shot. I mean, I'm taking key.
Oh, okay.
No, but that's not the way I should. There were capital N messages, yeah? And I encoded them, used the channel, and decoded them, okay? These capital N messages are completely deterministic. There's no probability, nothing in them. In thinking about the channel, I generate things IID and construct my code, etc. But that's a different matter, yeah. Okay, so thank you for your patience. I don't know how useful it was, but.
All right, so let's thank Jaikumar.